I wrote my PhD about robot-compliant motion based on human skills, and I have been looking at this in the very early 90s, and I think a fascinating topic and progress which have been done in this topic. Now, joining KUKA, coming out of research, I think 8 years ago, we can now say that a few things have been moved on in robotics. Now I have to charge this for a second. Okay, so I would like to talk about new robotics at KUKA, which is basically somehow connected to technical and societal challenges for robotics in industry and service. And I think we also have some significant progress coming out of the robot industry, and which could give some contributions back to research. And I would like to talk about this. Well, coming here to Karlsruhe, and I really liked the idea and the opportunity to talk here. I said, well, let's prepare. And I looked at Anthropomatik, so what's that about in robotics? So out of the homepage from KIT, I saw the major objective is to design, implement, and evaluate highly usable and accepted anthropomatic systems to improve humans' quality of life. And I really liked this idea. And of course, when you look at the picture, there's a lot of things about interaction, about perception, about action, how to move things around, but also when we talk about products going into this direction, it has to take care about safety and responsibility. And for the moment, for the time being, this is industry. And I would like to elaborate on this now, but looking at the challenges. When you look at the societal challenges, and I just want to pick out the aging society as an example, we are running in a tremendous problem. 25% of European citizens are older than 65 years in 2020. We have twice as many 80-year-olds. We have rising costs for social and health care, and I know that I looked at the figures because of some discussions. In Germany, in 2040, if you want to take capital to make the assurance for health, we have estimated 420 billion euro, 420 Milliarden Euro, to have actually capital which are looking for investments to have this assurance for these things. So this is a big step. We have dropping workforce and we have all the employees. And how can we address this? The European Union has recognized that, and it's a really, let's say, good exposure for robotics that we have been able to achieve a technology platform. Europe looks at its technologies based on technology platforms, and robotics has its own technology platform, and the coordinator of the platform is my colleague Rainer Bischoff. KUKA took the lead into these platforms, but actually is embracing all the other industries like industrial robots, professional service, domestic service, security in space, all them joined together and writing and publishing the robotic visions, basically a strategic product-based roadmap that should come throughout the years. You can download this, you should look at that, but the outcome is quite interesting. When you look at the application out of the industries, we have the worker, the co-worker, so worker somehow autonomous, co-worker in cooperation with the human. We have some logistics, autonomous logistics, surveillance and intervention, exploration, inspection, and edutainment as the combination of entertainment and education. And I think when you want to address these issues, the area of research which you want to address in your, which are already addressing that, which are in the focus of anthropomatics and robotics, are excellent drivers to put forward into these areas. Now, when I look at this from a product point of view, I have the following view. I look at economics, affordability. First of all, if you can't afford, you won't probably buy it. Safety, safe human-robot interaction, sensitivity, collision detection. Then functionality. We need to be mobile, we have to manipulate, localize, and navigate. Then, if it's not usable, nobody will buy it, or the thing will be in the corner. So multimodal interaction, use of knowledge, how to represent, how to learn, and dependability. And then there come the hardcore, let's say, disciplines which we have to really govern to make these possible. We have to be good in software engineering, in real-time software engineering, distributed control systems, sensor event-based control, so no robot language. KUKA robot language, other robot language, no Pascal-based kind of languages anymore. Event-based programming of these robots are necessary, whether driven by a human, by the expert, or whether driven by a learning system. And the mechatronics integration paradigm, first of all looking at mechatronic optimized design, but then integrating sensors and electronics to get very compact systems. And what I would like to take you home from my talk is, in part one, I would like to provide you some insight about our new product generation. It's industrial robotics, and we have showed it at the Automatica 2010, dead boring, but the technology inside is the first step into these new areas of service robotics. And in part two, I would like to provide some answers how to address these new challenges through products, the first products of KUKA. Now, let's have a look at this product specification. Highlighted in orange are the topics which are somehow and specifically addressed by this new product generation of KUKA. And this product generation consists out of basically the marketing, let's say the overall topic which was presented was automation becomes easy. And actually this is it, what is the main result out of this technology. But thinking from a technology term, we had to make our robots lighter. We want to replace the main robots which are used in the industry, in the automotive industry. So the actual one is 10 years old, we can do a better job. We actually had to reinvent PC-based control. The result is the KRC4. We went into the development of a smart pad. We had a big discussion whether to develop our own interface. When you consider that you have iPads and iPhones, that we came up with the same solution, looking at the vertical solution, was maybe not was not planned, but showed that we did a good job in looking at the specifications, and it helped a lot when iPad came out, and we had chosen the name SmartPad, and we had chosen the solution. And of course, some software, engineering software. And I would like to point out just two things: the robot mechatronics and the controller, how we reinvented PC-based control. Now, looking at, I have to apologize, the translation here, that is not right, but mechatronics design KUKA. When you look in 1980s robots, and you look at the Serial 2000, this robot is now in the plant. When you look at the big automotive plants, they are working as the main robotic horse, let's say, doing the jobs. Then, actually, there was already a dramatic decrease of weight, a dramatic increase of performance, but also, let's say, in pricing issues, of course. You can think here, there's a big issue of a lot of mechanics, less mechanics, and the new generation is even lighter, is smaller, has a bigger performance, and I can show you how this translates. when you look at the robot, industrial robot, so we have less weight. We have from here to here minus 160 kilogram. We have less volume. There are all mechanical reasons for that, how we achieved it. But it was not mechanical discipline, it was the discipline of looking at motors, looking at gears, looking at computation to do these optimized optimized robots. And we increased the payload from 240 to 300 kilograms. And that turned out very well, and this robot generation is now replacing this one and giving us a very good, let's say, starting point to renew and to be competitive in the very hard business of industrial robotics. Okay, somebody might think it's a new product, but the exciting thing in the background is that the mechatronical design has been really going through. We have went through models, through control models, through mechanical models, motor gears. We looked through control engineering, and so the cycle has been closed, and based on this closing the cycle in the design circle, we were able to build this robot. So it's a mechatronic product, even electronics is not included. And based on this knowledge, we can go further on. That's the message. Now looking at the controller type, when you look into a typical plant, on the motor industry, for example, you find a robot cabinet, you find a cell-level controller, PLC, you find maybe some external access amplifiers that do some fluid dispensing access, for example. You will have maybe a PC running the process control, and you have a safety PLC looking for the safety in the cell. And then you try to synchronize that all together through networks, through field buses, and it's easy for handling, but if you want to do really complex tasks, you have a lot of time lags in between there, and you're trying to engineer the hell out of investing a lot of time to make it work. It's not really the thing how you should work it. And we came up with the idea of inventing PC-based control. We have so fast PCs. Why don't we come up with a robot PC controller that can do the robot control, that can do the cell control, that can do the motion control, that can do the process control, and here comes the hard one, the safety control. If you have this on one PC, synchronization, data consistency, and communication is a piece of cake. It's easy. Yeah? Now, but this is the hard part. How can you do it? And we started with the first thoughts into this development in 2004, and we did some drawings. I don't have it with me, but actually it turned out to be exactly the same way how we now are showing the product. It took a long time for KUKA to come up with this development. Looking at the old PC-based control, the KRC2, which is now in the plant, you see it's PC-based control. You know that we have a real-time operating system. On top of the real-time operating system, we have Windows to do the human-machine interface. But altogether, we had 7 bus communication systems. I'm not explaining you in detail. I can do it. I choose to not do it, to spend a little bit more time doing showing you other things. But and there's a nice translation slide how we did it, but I took it out, it's too much. But looking at the core of the PC, we're running Windows XP embedded for the human interface. We have a real-time operating system, it just happens to be ThesWorks in combination with Windows. We worked early on prototypes from the symmetric multiprocessing technology, so that you can choose and assign, let's say, computing power to the cores. We have 2 controllers, which are the systems controller running in different timings, including these other controllers like process controllers and PLC. We took out the signal processing card and moved the primary control loop on the other core, and then for the safety have 2 instances of safety control loops. It's a kind of a PLC, but it's actually, you can also program it with C++. So basically we came up with, on 2 cores, with 5 operating systems. And with that compact technology, we were able to come up now with a new architecture, which really just has one bus system. It's one real-time measurement system. Everything runs on software, no hardware cards. Good news for us in industry, no more Siemens cards, hardware cards, which we have to pay hard for. We can do it in software, so we can get a little bit money for us back, you know, because we're really in the sandwich as a robot manufacturer. But with this architecture, the nice, exciting thing is I can take data from here to here, safe, in a safe network, with a safety integrity level, whichever I need for the application. And the key features, as I said, is the usage of multi-core, the usage of 100 megabit real-time Ethernet, and the safety, the integrated safety. And with this architecture in mind, and a lot of my developers come out of research, this was clear that this is something you can take over into service robotics, into new applications. Now, looking at the safe robot technology, there are a lot of applications that require safety. Whenever you take out the fence, you need to have a safe robot and to gear with the safety technology into the application. And of course, we are interested in this part, assembly as well, but also entertainment, which has been, let's say, it's now developed for, let's say, flight simulation, but there's no fences in these applications. And it becomes quite clear that with this controller architecture, together with this mechatronic design, which I showed you, we want to extend, and we were going to extend this architecture and take this, put it into the lighting robot, put it into the mobile system, and combine it to mobile manipulation system. Finish part one of the story. Let's go and move to part two. And here we would like to provide some answers through these new challenges. When you look at service robotics, and we have been looking at that for a long, long time, and I think a lot of expectations were connected to service robotics. But really, it's fascinating that I think we are now moving towards the paradigm of mobile manipulation, combining the manipulation, lightweight structures, with mobility, whether it's like mobile robots or humanoid robots, walking robots, that doesn't matter. And now you can really have hardware addressing these nice applications. And looking at the product specifications for this area, we look at the blue colored, we look at sensitive robots, it's collision detection. We look at functionality, mobile manipulation, localization, and navigation. We look at sensor event-based control. We need new control paradigms, new controllers to work around with that. And of course, the mechatronics integration. And I think one example, and there are three products I would like to show you and discuss about and think about, which could move us and give some answers into this direction. They're not ready yet, but the thing is, I mean, the products, yes, but there are no complete systems yet for elderly care, for example. But based on these systems, you can develop prototype and to make this arm smaller, to make these mobile platforms adjusted to the task from a factory floor to a hospital or to a home even. That is doable. It's in the view of things. And that's the exciting thing. So what we need are good specifications, good sensing, and a good software for it. And we have the platform for it to implement it. And this is, I think, the exciting story about it. Now, I don't have to tell you a little bit more about the lightweight robot that has been presented. You know, it's coming out of a technology transfer from DLR. The contribution of KUKA really is to go through a hard time in putting the product into the right quality. Also to tell the customers what you can do with all these compliance controls, to work it out. And it's different whether you're doing it in research or whether you're telling it the customer. And then by telling the customer, explaining the customer what the robot can do, they're getting new ideas. And I think we have the last 2 years worked very hard in different areas to apply this technology. And of course we have provided the robot into research, but we're also looking in the automotive industry here. Again, we're back in the automotive industry, but with new applications. And of course, in the general industry, this is the area of small and medium enterprise robotics, and a very exciting field about medical robotics, which I'm not going to elaborate on that in my talk right now. But looking at the automotive industry, because this is an example which shows nicely how to use the compliant features, that is the assembly of a gear. That task is done manually. Now, here you see a two-armed manipulation taking this gear component inside. It's quite a difficult task because you can squeeze your hand in while doing it manually. You can basically touch with the gear teeth the housing, and then you will have some quality problems. You hear noises after 10,000 kilometers, and you see how the compliant motion manipulation features are used in the assembly, that you have some, let's say, dithering and some force or compliance stiffness sinusoidal that are helping to do the insertion. Also, you see that we're not carrying the whole weight. We're using a balancer like a human here, and this is then used by the two-arm robot system. I have to acknowledge here that this is the work of our customer, Daimler. Daimler. Yeah. And so we are helping them, but the looking at the functionality and really implementing it was done at Turkey, and it's a very exciting field that you can think a lot about how to advance assembly in the automotive or in the tier 1 industry with this type of products. Now, looking at some other products, the nice thing is when you look at the OmniRob system, like with its mobile robotic, that you have some scalability to some smaller systems when you what I will explain shortly, but in the combination of those, you can really start out and do prototype tasks. The robot can autonomously localize and navigate. There's full interaction, 7 + 3, 10 degrees of freedom interaction. You can see some nice air hooks here. You can see new devices. So once the inherent safety architecture is implemented, I think we can make use of all these nice interaction devices here at the iPhone. And you can also see this on prototypes task. This is basically the display of the Automatica 2010. Now with these systems, whether 1 arm, 2 arms, 3 arms, I think we can provide to do prototyping. We're currently working with industry to put these in place. So we're really trying to push that based on the products we have right now. Now, some crazy project, U-Bot. This was a project which was started 2007, 2008, and which almost got, let's say, broken down or shoot out in 2009 in the economic crisis, but due to some EU funding, we were able to really carry on, and now we are happy to present this product. The idea is to look at mobile manipulation and provide a platform with a small robot. Small robot like the plastic robots we give for our customers that they like. Okay, this is a KUKA robot, but now with motors. And we said, let's build a robot that has a nice motion performance and costs, let's say, 1,000 euro. But that didn't work out. It's just not possible to build this robot with the motion performance for $1,000 or €3. It's not possible. So we came up with a different solution. It's a little bit more high quality, but our approach was we want to have the same motion quality as the industrial robot. It's a 5-axis machine. It has an inbuilt gripper system. It has a weight of 7 kilograms. Can have a payload of 0.5 kilograms. So here the scaling is not as nice as with the Leica robot or with our big Titan robot. But anyway, it runs on 24 volts. It can be put on a platform. These platforms are using our Omni wheels, which we have also in the Omni and on the larger Omni Move platform. And you can combine those things to do prototypic mobile manipulation tasks. And you can combine it even with 2 arms. The reason why we do this is first of all to give research an open platform. You can download any software on that. Could be some software out of the US, some initiatives. There's one initiative from Bricks. I will show you some slides on that. This is some more technology inside. You see the robot moving, and also some application connecting a Wii controller to do such kind of games. But you can basically put software on it, write your own software on it. So it's not a controller software provided by KUKA. We have some ideas for our own software as well, but it's not out there. And based on, let's say, for example, best practice in robotics, it's a new project which we have a lead for. We are taking these platforms now and putting out challenges, and these challenges was done on a workshop in Spain just a few weeks ago, and it gives back, we're giving some back to the research a possibility to add to these robot sensors and to make research in mobile manipulation, even incorporate mobile manipulation system to a reasonable, affordable price, and to have, let's say, open software structure to be innovative on it. And this is, I think, the message. The second thing is we want to take this into education. One important thing is really to show young students, even on the gymnasium or high school level, that they should be fascinated about technical things, about engineering. And I think this is a very, very nice structure, and we're working hard on putting out a curriculum for that. And third of all, it's interesting when you show this to the people, they start, I have an idea, I want to do this or this job in industry with it. So there will be some strange customer community who are taking the system and doing prototype tasks. And we found out that it's actually a quite good preparation for the industry to talk about mobile manipulation. They're taking the system, trying out things. Of course, it's maybe not useful because it's this height, so maybe we get a large one, but for prototyping, it's perfect. And so this is the triangle of education, of research, and prototyping of mobile manipulation tasks that is actually addressing these efforts, these products. Let me come to the summary, to the conclusion. Let's say we have remarkable societal challenges, but they also offer remarkable business opportunities for robotics, and also on the side of industry, because the workforce is getting older, has to work longer, and for service, even in the home area. We see our new industrial product generation as the architectural base for building surface robotics. That is an important point for us as a company, that we have done our architectural work. KUKA is taking responsibility and leadership. As I explained, the European Robotics Technology Platform is coordinated by us in some of the important EU-funded projects. And you know that we are heavily involved into industry-academia collaboration. Also doing technology transfer by persons. Our lead designer of this mobile manipulation system is Dr. Putniak. He's also here with us. He was the co-designer of AMAR 2. He joined us 2 years ago, and we think we can close the gap towards personal robots going from classical industrial robots to these hybrid robots and make them mobile. And I pointed out the innovation triangle: education, research, and entrepreneurship, which we really want to push with these kind of new products. Now, the important thing for KUKA is to do this in the future. It's for us very important to get the focus. And the message is also that we have long thought about how to put focus into it. And the only possibility is really to give this type of robots a different setting, also in our company. So what I can present to you is that this new robotics at KUKA will be put into a separate company called KUKA Laboratories. This company is not a research company. This company is about products, without robots, without fence, robot going into also non-industrial applications. And so I can say this company is dedicated to human-robot cooperating systems. And I'm looking forward to work with you here in the focus. Thank you very much for your attention.